Hi, everybody. This will be section 6.2, which is the assignment of probabilities. And looking at my syllabus, it looks like we have two more lectures after this one. Again, I'm going to try to get this one all done in one lecture and have this uploaded to you. Okay, first of all, we need to talk about what probability is. And probability is a numerical measure of the likelihood that a specific event will occur. So what we do, we put a number to it, and depending on what that number is, that shows you the strength of the probability. So a couple thoughts here. First of all, the number is always between 0 and 1. And the closer the probability is to 1, the more likely the event will occur. The closer the probability is to 0, the less likely it is to occur. And as a matter of fact, if it had a probability of 1, that means it will happen. And a probability of 0 means it will not happen. So if somebody says you have a probability of a 2, you know that is impossible. Because it can't be bigger than 1. It can't be negative. So, one of the things we hear is you got a probability of 100%. Well, remember, 100% is 1. So if it's 100%, that means it's going to happen. That might keep things in perspective. Also, as we go through this, probabilities could be written as decimals or they could be written as percents. So if I had something that said, let me make one up here. If I said something like 57%, remember that's the same thing as 0.57. We use percents because it kind of makes more sense to us because we do, we think of things as scales of 0 to 100 as opposed to 0 to 1, but they're interchangeable. In everyday life, we use percents quite a bit, and as you go on in probability and you start talking about statistics, we tend to go more towards the decimals. Okay, so now let's talk about different types of probability, and I don't want to dwell on this, I just want to touch on it, and some of them are kind of vague. But the three types of probability are: 1, logical probability; 2 is empirical probability; and 3 is, it should be judgmental probability. I got judgment, make it judgmental. So going back to logical probability, this means you can look at it and you can think about it logically and figure it out. So like if I had the probability of heads, I always like to think probability is good out of total. So if you're flipping a coin, how many heads are there? Well, there's only one out of how many? 2. 1 out of 2. Oh, and sometimes we do probability in fractions, but not often. So that would be 0.5 or 50%. That means 50% of the time that you flip the coin, it should end up being heads. Okay, in a likewise manner, it is possible to go through and find a probability getting a full house in poker. I'm not going to go into it, but there is a way of doing it. And winning the lottery, well, if there's 1,000 tickets and you have one of them, then maybe that probability would be 1 over 1,000. And that would be 0.001, which is 0.1% if you want to think of it that way. Okay, so logical probability, you can figure it out in your head. Now, empirical probability is a little different. This has its roots a long time ago when, God, this is going to sound bad, but they used to take mortality rates, and they would calculate how often people died, when they died, what age they died, and if they had a disease, when did they die from that, and things like that. So what they did was they kept track and they started writing down the results, okay, and coming up with some numbers so they could come up with that. Well, that's what empirical probability is. And I got a real good example I'm going to do here in a second, but it is found by sampling, meaning you do things over and over again, and then, you come up with your numbers. So here's a good one. So how long will it take a light bulb to go bad on you? Well, let's say we did this, and for the light bulb, we kept it on for as many hours as we could. So depending on how many times it made it over 1,000 hours out of the total, that would be your probability. So you could do it by testing it. Same thing. What's probably a person selected at random will be a smoker. You've seen people at the mall taking surveys and things like that. You could do it in that fashion. And same thing, taking a drug that will work, which is kind of common right now with the pandemic going on, and they're trying drugs, and they have these trials going on, and they're keeping track of all that data. And when they get that up into the 90%, then all of a sudden the Food and Drug Administration are getting to a point where they may approve it. That's where we're at right now. Okay, and then there is judgmental probability. And sometimes this is what I would call just an educated guess. Okay, what's the probability the Colts will win the Super Bowl? Well, I don't really know. And you may have your thoughts, and somebody who follows football may have a better idea than other people that don't. But basically, it's just an educated guess by that person. I can give people what I think it would be, but that doesn't necessarily mean that's what the true probability is. What's the probability a Democrat will be elected as the next president? I don't know. I'm not going to touch that one. And what's the probability you'll get an A on the next exam? Well, your idea might be different than what my idea is. But everybody's going to have their own guess at what they think that probability is, and that's what judgmental probability is. So let's see. I'm going to go to this. I've kind of got this out of order. So when you look through your outline, bear with me. I'm trying to get papers moved around here. I've got a couple examples here that hold on. I'm trying to get situated here. I'm sorry. Okay, so here's this example has which type of probability, logical, empirical, or judgmental, fits for the situation. So what's the probability it will snow tomorrow? Well, a lot of times that's just up to what a person might think, but sometimes, you have the weather people, and what they do, they do these tests over and over and over again. So since they're doing these tests, they're collecting data. To me, that would probably be empirical, okay? But there's a little bit of judgmental in there too. It's a little bit of both. What's the probability in B? What's the probability that China will win the most medals in the next Olympics? Well, again, I think that's going to be more judgmental. But you could make that judgment off past performance or other data that you might collect. And if you're thinking that way, then yes, I could see that being empirical. What's the probability a person will hit their next free throw? I think without a doubt, that would be empirical. I say without a doubt. I mean, if you're keeping track of statistics, and they hit 90% of the free throws, that means there's a 90% chance that they're going to hit the next one. That'd be the probability, 90%. If you're basing on your own judgment, though, that could be judgmental. That's why I said some of these are a little fuzzy. Okay, what's the probability of taking a particular drug will cure a person's cancer? Well, we just talked about that. Eli Lilly here in town. I know they do a lot of trials. So based off the trials, that would be empirical. How about E, the probability of getting a sum of 7 when tossing a pair of dice? Well, you're going to find out that later on is going to be logical. There's a way of doing that. And what's the probability that the NASDAQ, which is a way of measuring our economy, will increase by more than 10% in the next year? You could probably use empirical a little bit, but I think for the most part that's going to be judgmental. I'll put a /E, meaning probably more judgmental, but maybe a little bit of empirical. So as you go through these, it's a little hazy. Okay, so now let's go back to this. I skipped over this part. Okay, let's say the probability of heads. We talked about a second ago. It's 1/2 because you said, well, heads is one out of the two choices, or one of the two things that could happen. So, is it really 1/2? We talk about loaded dice sometimes, and a loaded dice. Hold on, I'm trying to do two things at once. I'm sorry. Okay. If that coin was an honest coin, then yeah, it'd be 1/2. Sometimes it's not. Well, what if we toss that coin 10 times? This is how you test to see if it's an honest coin. How many times would you expect to get heads? When you flip it 10 times, how many times do you expect to get heads? Well, half the time, right? 5 of them. Okay, that's logical. Okay, logical probability. Okay. Now, let's say we flip a coin multiple times and got the following results. So, I've done several of these, and I've already got the numbers, but let's say I flipped it 10 times. Do you actually get it where it would come up 5 every time? Probably not. Let's say I came up with 4. That's a realistic guess. And if I want the relative frequency, all I'm going to do is take the 4 that I got and divide it by 10, and that ends up being 0.4, and for reasons you'll see in a minute, think of that as 0.4000. Okay, well, what you find out is 10 times is not enough. Okay, what if we flipped it 100 times? I flipped it 100 times. Let's say I got 58. I actually did this and got these numbers. So that's 58 over 100, and 58 over 100 is going to be 0.5800. So we're still pretty close to that 0.5 mark. Okay, let's say we did 1,000 times. And when I did it, I had 492, which you would expect 500, right? But as a decimal, it's still 0.492. And I'm just going to fill in some other numbers. If I did it 10,000, I'm just going to put 10K or 20K or 40K, 40,000. There's a way of doing on your little TI-83s if you want to do that. You don't really flip them that many times, but you can do it and it'll give you the answer. So this answer came out to be 5034, and this is 10,024, and 20,032. So as decimals, I'm getting these numbers, and these are easy to see. I'm going to just truncate that. Wait a second. I'm sorry. Don't know what those do in there. This is 0.5012, and this is 5008. So as you can see, no matter how many times you did it, all these numbers are really pretty close to 0.5. Now, let's do one more thing. I'm going to change pins. Otherwise it's going to start smudging together. I hope you can see this okay. Okay, so the difference between this and 0.5 is going to be 0.1000. The difference here, in other words, how far away from 0.50 is it? It's 0.0800. This one's going to be 0.0080. There should be a 0 there if I put it in there. This one's going to be, wow, 0.0034. This one's going to be 0.0012. And this is 0.0008. Now, depending on which way you were subtracting or whatever, you know, one of them might have been negative, but all this is the difference between that and 0.5. Okay, here's what I want you to notice. Okay, we were 1/10 off. But notice as you go down, see how these numbers get smaller and smaller and smaller? What that tells you is the more times that you do this, the closer you actually get to 0.5000. And that's what they do with empirical probability, is they do it over and over again, and eventually those numbers get closer and closer to what they should be. So we would say this coin, since it is getting closer to 0.5000, that is a fair coin. Okay, and just to point this out, relative frequency, we simply divide and come up with that number. That relative frequency, as we go on, that approaches something, and that becomes closer to the probability. That's the empirical probability. Okay, let's see. I'm going to skip over. Let's go to this next. I want to talk about flipping. We're going to start putting together distribution tables. And in this case, we're going to flip one coin. So what could happen? Well, the sample space becomes just simply heads and tails. So the probability of heads would be 1 out of 2. Heads is 1 out of the 2. Tails is 1 out of the 2. And these are the only two probabilities. So if you add those together, those are going to add up to 1. So 1/2 plus 1/2 is equal to 1. 1's the magic number. Now here's some questions. What's the probability of getting heads? It's up here, it's 1/2. What's the probability not getting heads? Well, if it's not heads, then it's tails. That's 1/2. What's the probability of getting heads or tails? Well, it's got to be one of the two. So that means you got what I call 2 good out of 2 total. That's 1, or 100%, which makes sense. You are going to get one of the two, right? What's the probability of not getting a head or not getting a tail? If I don't get a head, that's tail. Yeah, this is probably too confusing. The answer is going to be 1. Okay, so now I'm going to jump to this. These are all out of order. So each of these probabilities here, like there's only 2 of them, so consider that one like P1 and that one P2. And if you had a whole bunch of them, what you notice is all these probabilities are going to be between 0 and 1. Okay, so one of the properties, this fundamental property 1 they give you, is each of those probabilities, P1, P2, P3, as many as you got, are always going to be between 0 and 1. And then if you add these probabilities, what do they add up to? Well, that's fundamental property 2. They're always going to add up to 1. So So if I take p sub 1 plus p sub 2 plus p sub 3 all the way up to the last probability, if I add them all up, I end up getting 1. So those are the two fundamental properties that they throw at you. Okay. Let's get away from that. And let me hang with me. Okay, let's go to this one next. This got botched up when I copied. It's probably going to look okay to you, but it came out of two different pieces of paper. Okay, so this time we're throwing a single die, a little cube, right? So when you throw it, you could get a 1 or a 2 or a 3 or 4 or 5 or 6. Now these are what they call equally likely. If it's a fair cube, it's equally likely. So that means if they're equally likely, that means the probability of each one of these is going to be 1/6, because getting a 1, that's 1 out of the 6. Getting a 2, the 2 is just 1 out of the 6. Getting a 5 is just 1 out of the 6. So each of these guys are all 1/6. What do you get when you take 1/6 plus 1/6 plus 1/6 all the way down to the bottom? What should you get? 1. They're always going to add up to 1 in a probability distribution. A probability distribution simply means you're going to take all the possibilities, put them over here. Sometimes they call this, let's just call it x, and this would be p of x. Okay, now what's the probability of being odd? Well, that means you could think of that as 1 or 3 or 5. And what you find out is or means add, so we're going to take 1/6 plus 1/6 plus 1/6. That's going to be 3/6, which is 1/2. And that's what you'd expect. Half the time it's odd, half the time it's even. Okay, what if I said the probability of getting a number greater than 4? Could it be 4? No. But it could be 5, it could be 6. So you're going to take 1/6, that's probably a 5, plus the probability of a 6, that's going to be 2 over 6, which is 1/3. And for these, I'm just going to leave them in terms of a fraction. I'm not going to change it to a decimal. What's the probability of getting a 7 when you roll a die? Well, you can't. There are no 7s. So that's 0. Remember, 0, you can't do it. Okay, this one says, what's probably getting a number between 1 and 6 inclusive? So that means it could be 1, it could be 2, it could be 3, it could be 4, it could be 5, it could be 6. That's all of them together. It would have to be one of them. So that answer is going to be 1. Okay. Okay, now I'm going to switch again. I'll come back to this page, and I want to talk about this page next. Going back to here. Two more properties, the addition and the inclusion-exclusion principles. The addition principle we just did. So if E consists of a finite number of outcomes, S, T, U, all the way up to Z, and actually it could be more than that. But from what we got there, okay, E represents each of these things that could happen. These are the different outcomes. So if I want the probability of E, that's going to be the probability of the first one plus the second one plus the third one all the way up. So it's individual probabilities. And I just did that on this example. I left this one on here. The probability of getting one of those I simply added. Or the probability of, what was the other one? I'll just write it down. When I was rolling the die and I said, what's the probability of it being, let's say, odd? Okay. Then that became the probability of 1 or 3 or 5. And we're simply just going to add those up. I'm out of room, so I just put a half over there. But I did that in the error problem. That's what the addition principle is. So we've already done an example of it. Okay, and then I'll do this one a little bit more in a bit. The inclusion-exclusion principle. This is going to look very much like a property we had in the last chapter. This says the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E and F. Last chapter, we had a formula that looked like this. The number in E union F, I think I used A and B though, is the number in E plus the number in F minus the number A intersect B. Kind of scrimping that in there. Or E and F. Okay? And if they're mutually exclusive, then it's the same formula. I just dropped that one off. You'll be pleased to know that last chapter we had 3 sets at a time. We won't do that here. It's all going to be 2. At least you're not going to have any Venn diagrams to make it look that way. Okay, more on this one in just a second. Okay, so let's set up a different type of probability distribution. On this one, we're flipping a coin twice. And if you'll remember, when you flip a coin twice, what could happen? Well, the first time it heads or tails, the second one's heads or tails. Okay, like that. So we got heads, 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 tails, tails, heads, tails, tails. Each one of those is an outcome, and that's what I got right here. That's where those came from. So when I'm flipping a coin twice, these are the things that could happen. Now, on this one though, we're talking about how many heads occur. Okay, so this would be the number, if you want to write this, the number of heads. So when you're flipping a coin twice, you could get 2 heads, or you could get 1, or you might not get any. So the probability of getting 2 heads, when you look up here, I've got 4 different outcomes. The first one is the only one with 2 H's. So that would be 1 out of the 4, so the probability is 1/4. That might be a little small for you to read, I can't tell. Might have made it worse there, but that's 1/4. The probability of getting a 1, that one works. You got 1 head and a tail. Here you got a tails and a head. So those 2 work. That's 2 out of the 4, which is 1/2. And the probability of getting 0, that's the same thing as 2 tails. The probability of getting 2 tails would be 1 out of 4. That's what I got. What do you think you get when you add them all up? That's right, 1. You knew that. Anytime you add them up, and sometimes, you know, if you're trying to figure all these out and you come up with your probabilities, if you add those up, that's a way of checking to see if you did it correctly. Okay, what's next? I want to go to this next. No, I'll do it here. Let's go ahead and do this. So now let's say we're tossing 2 dice. And when you throw 2 dice, what you usually do is you add them. And you come up with sums. So my little chart over here that I put together, if let's say I have a green die, that's why those are in green, and a red die. So if I have 1 on the green and 1 on the red, it gives me a 2. I say red and green, that way you can distinguish. When you roll them, you can tell what you got. So anyway, 1 plus 1 is 2. If I got a 1 on the green and 2 on the red, that's 3, and so on. So 2, 3, 4, 5, 6, 7. Once you get going, this is easy to fill out. What I would suggest for you to do right now is copy that chart down, pause your video, write that chart down, put it on like an index card, and keep it handy, because you'll use that a lot on some of these problems. Okay, now, over here we got a probability distribution started, and my outcomes are determined by the sums. So you'll notice in my chart here, the smallest sum was a 2. I've got 3s, 4s, 5s, all the way up to the biggest one, which is 12. So I've got those listed here. Now, the probability of getting a sum of 2. Now look at your chart. How many sums of 2 do you have? I've got 1 out of how many? 36. Not 12, but 36. So that probability is 1 over 36. The probability of getting a 3, how many 3s are in the grid over here? Well, there's 2 of them. Now, you don't count that one, you don't count that one, because that's what you had on the individually die. So you've got these 2 right here. So that's 2 out of 36, and fractions you always put in lowest terms. These are odd fractions. That's why a lot of times they'll write that as decimals. To get a 4, there's 3 4s, so that's 3 out of 36, which is 1 over 12. To get a 5, that's 4 over 36, which is 1/9. To get a 6, that's 5 over 36. Can't do anything with that. To get a 7, there's 6 of them there. 6 out of the 36. All I'm doing is counting the 7s. 1, 2, 3, 4, 5, 6. Everything on that line right there. So that in lowest terms is 1/6. And then what you'll notice is we've kind of been going uphill. Everything comes downhill again. 5, 4, 3, 2, and 1. Just filling in the numbers here. Now let's answer some questions down here. The probability of getting, we're talking about a sum here, the probability of getting a sum of 7. So I look up here, here's a 7, looks like that's going to be 1/6. We'll just leave it as a fraction. The probability of getting a 1, well, you'll notice up here there are no sums of 1, so that's going to be 0. The probability of 5 or 6, well, the probability of a 5, and I'm just going to write this as 4 over 36. And the probability of getting a 6 is 5 over 36. What are you going to do with those two numbers? What does OR mean? Add. Anytime you see OR, think add. So 4 plus 5 is 9 over the 36. In lowest terms, that's going to be 1/4.